Let us continue our lecture, and as I promised, I will explain this important point about what beauty could not be, the third point. So it's something so-called non-instrumental aesthetical judgment. What I mean here, that in these beautiful and ugly drawings, sometimes mathematicians say, when you ask them why one is more beautiful than the other, they say different things. They make a list and they say that yes, well, the first one it has this nice structure. You can see clearly the symmetry, the structure. They say the same what the psychologists say and cognitive scientists say. But also they say, and we kind of used to this. It's a traditional drawing. It's convenient. You can see it in every book. It's easy to refer to it. So at this point, they talk about some practical gains from using this drawing. So it's useful for them in instrumental, practical terms. And they have some positive emotions because of this practical gain, these practical benefits. So the thing is, when they are making an aesthetical judgment about this drawing of the Peterson graph, they may react to perceptual beauty, yes, perceptual visible symmetries, and presumably not only because a lay person may prefer the other one, the ugly one, but they choose this one. So there must be some mathematical advantages which they appreciate, but also they may add these emotions that's good for them when they use this graph, that it's in practical terms. So this kind of practical emotions add the emotions of the pleasure of seeing this graph, and at the end they say that this is a beautiful drawing of the Peterson graph. But I think it's important to distinguish these practical reasons, and despite they come together, they are not aesthetical contributors. You see what I mean? Yeah. So because these practical reasons are not related to the power of the mathematical entity or the drawing. It's something instrumental. When you look at the plate with fruit, with beautiful Brazilian fruit, you say, oh, this mango is beautiful, this papaya is beautiful. You are making aesthetic judgment, but you have to distinguish that it's not about you wanting to eat this fruit. Yeah? You're really judging the fruit, the properties of this fruit. It's not your practical, selfish gain, selfish interest that you want to eat this fruit. And that's why, and you anticipate the taste, for example, and the nice feeling in your stomach and in your mouth, for example. You are talking about the visible beauty of the fruit. Yeah. Same here. We have to differentiate these practical reasons, which can create some positive emotions, which can help a mathematician to arrive to an aesthetic judgment, but they are not contributors of the aesthetic judgment. Is this clear? Yeah. So far we were talking about visible perceptual properties of graph drawings, and in particular of drawings of the Peterson graph. Now I stop talking about visible properties and turn to mathematical properties of the mathematical entity, the Peterson graph. Yeah. Because there could be a question from you, for example, you may ask me, and how about those mathematical objects which do not have beautiful visualizations, for example? And also you can ask, okay, this traditional Peterson graph is considered as more beautiful than the ugly one, but a lay person would say, well, this is not true, so that means there is something behind a mathematician's judgment about the traditional drawing of a Peterson graph, which is related to more than just perceptual properties. Right? How about that? I think that invisible symmetries, those which we can see, they contribute to the beauty, not of a visual perception, but of the object represented. And the object represented is the Peterson graph, the abstract mathematical object. How can symmetry contribute to intellectual beauty? Well, as I said, symmetry helps us to grasp mathematical structure, and symmetry implies other significant properties and conjectures. The first point we have discussed already, yes, I said that when you have a clearer drawing, it's easier for you to grasp the structure, and you have more opportunities to appreciate the beauty, to have the pleasure of the beauty of the abstract, of mathematical. But also, symmetry implies other significant properties and connections. Let me give you some examples. I promised you that you will learn some mathematics from my course, so here it comes. So it turned out that the Peterson graph is one of 4 possible Moore graphs. Moore graphs, what they are? Let me explain you in simple words. Moore graphs have some mathematical properties, which are a diameter equals 2 and girth equals 5. What does it mean? These are just some parameters of the graph. Diameter is the path, the shortest path, which connects any point, or any vertex of the graph with the most distant one. So, for example, in this pentagon, there are 2 ways to go to this vertex, from this vertex to this vertex. One way is to 1, 2, to go right, and one way is to go left. So the left will give you 3 steps, and the right 2 steps. And these are the most distant points in the graph, and the shortest path is 2, so the diameter is 2. If you look at the Peterson graph, it's the same. In order to go to one point to another, in order to come from one point to another, you only need 2 steps to get to any distant point in your graph. For example, from here to here is 2 steps, 1, 2, and from here to here is also actually 2 steps if you go by pentagon. Can you see it? So you can check any vertices, and it turned out that you can get from one vertex to another in 2 steps. So this is what the diameter means. And another parameter is girth. Girth is this. So it's the biggest. I think it's the biggest cycle in the graph. So the length in pentagon is only one cycle. So cycle is a loop in the graph. The loop in the graph. The smallest cycle in the graph. So the length is 5 steps. Here as well, the smallest is 5 pentagon. So for these 2 parameters, the mathematical question is, given these 2 parameters of a graph, what graphs can we construct? It turned out that there are only 4 possible. One of them is a pentagon. The second one is the Peterson graph. The third one is Hoffman-Singleton graph, which have 50 vertices. 50 vertices. And it's an open mathematical problem if the 4th graph exists. So this is an open question for mathematicians to solve. It's not solved yet. And remarkably, there are only 4 of such graphs possible, and the Peterson graph is one of them. So this is a rare property. This is an exceptional property. And this is an ongoing mathematical research. Another property is that the Peterson graph is not a Cayley graph, which means it's not a graph of a group. These are 2 drawings of Cayley graphs or graphs of groups. This is K5. It's also a graph of a group, a Cayley graph. This is our Peterson graph. And you can see that they are all highly symmetrical. They are very symmetrical, and Peterson looks very similar to K5. However, these 3 are graphs of groups, and Peterson is not a graph of a group. Why is it interesting? Why is it unusual property? Well. A group is an algebraic construction which can be used in order to study symmetries of geometrical objects. For example, this is one of the interpretations of groups. So, and a Cayley graph is a graph of a group. So, group is an instrument to study symmetries. Group reflects symmetries of a geometrical object in a combinatorial way. However, we can draw a graph of a group, so we can depict a group in a graph theoretic sense. And of course, these graphs are very symmetrical graphs, of course, because of course, I'm giving you only one interpretation of the notion of group, just because it's not mathematics, it's philosophy course. And what I want to stress is that one of the views of a group is that it's about symmetries, and therefore a graph of a group is a symmetrical graph, a very symmetrical graph. However, when you have a graph such symmetrical as the Peterson graph, you would have expected it could be a Cayley graph. It has these so many symmetries, 120 symmetries. It's highly symmetrical. However, surprisingly, it's not a Cayley graph. So this is kind of this property is very interesting. It's connected to symmetries of the Peterson graph, but it's surprising. It's unusual, and you can see it's so close to K5, which is a Kerry graph, but the Peterson graph is not a Kerry graph. Next interesting property. The Peterson graph is a non-planar graph. I mentioned this before. This property, a planar graph can be visualized on a plane without edge crossing. For example, this butterfly graph has no edge crossing. All the crossings are actually vertices of the graph. The Peterson graph is non-planar, and there are some proofs why it is not planar. And these proofs, some of them are based on the existence of some symmetrical configurations in the Peterson graph. For example, there is a proof that if a graph contains K5 or K33, well, this is another graph as a subgraph, yeah, then then it's a non-planar graph. And in the previous slide, you can see this is K55, exactly. So if a graph contains K5, then it's non-planar. There is a proof, very easy proof. And it's remarkable that this proof can be visualized. Yeah, if you look at the drawing, the traditional drawing of the Peterson graph, you can see that you can transform the Peterson graph into K5. Yeah, you can, for example, if you stretch the star up to the pentagon, yeah, and delete these edges, this is allowed to do, yeah, then you will have K5. And this is actually the proof why the Peterson graph is non-planar. Okay. I mean, and this is due to the symmetry of Peterson graph. Of course, if you have a drawing of a graph which is non-planar, absolutely, this is the proof. But if you don't have such drawing, you need a proof. You need a mathematical proof for this. And there is a proof using K5, which you can apply in the case of the Peterson graph. Is it clear? Okay. Yes, but however, it's interesting that there is a beautiful embedding of the Peterson graph on the cross cup. I can show it for you. So this is a three-dimensional video of an embedding of Peterson graph on this kind of surface in 3 dimensions. Here you have a screen which shows the sequence of drawing the edges. You can see now we are drawing the pentagon, and in a moment, and now we are going to draw a star. And the edge is connected to the star. So as you can see, it's very difficult to understand what's happening in 3 dimensions, right? And it's very difficult to see the symmetries in 3-dimensional video. And this is another reason why mathematicians still need to draw graphs in 2 dimensions. Here is another interesting property also connected to the symmetries of Peterson graph. If you take the traditional drawing and take the star inside and sort of twist it a little bit, rotate it inside the pentagon, you can stretch the edges so that all of them will have the same length. And this is so-called a unit distance graph. So the Peterson graph can be drawn in the plane with each edge having unit length. So you see all the edges are the same. However, it preserves the symmetry, at least rotational symmetry. So this is another remarkable property connected to symmetry of Peterson graph, and many more. This was just some small number of examples of a few from a huge list of properties of the Peterson graph. So here, David Joyce, a mathematician, is saying if you are talking about theoretical beauty, Peterson graph would top the list. Simple, but almost always counterexample to simple theorems you try to cook up. This is just a quotation from a mathematical forum, from a blog. As I said, in doing philosophy of mathematical practice, we have to look at what mathematicians say about their job. And here you can see that he is really referring to theoretical beauty. What he means here, he definitely means not the perceptual beauty of the Peterson graph. He really means the mathematical beauty of the Peterson graph, right? And what he is referring to is that it's a counterexample, and that it's highly symmetrical. Here is one more quotation about the Peterson graph. From Alejandro Ericsson. The Peterson graph is a beautiful graph, at least that is what graph theorists will tell you time and again. In spite of its small size, the size is relatively small. Yes, it's only it's easy to calculate and see everything. Only 10 vertices and 15 edges. Its structure is beautifully symmetric. And this has far-reaching consequences. And far-reaching consequences, I mean, some of the properties are listed, and also, it's highly symmetrical, as I said. It has many interesting properties. It's a counterexample to many conjectures. It's small but trivial. This is a sort of a sum up of what they are saying, mathematicians, why it is beautiful. And it's beautiful here, I mean, mathematical beauty, not a perceptual beauty. Oh, not at all. So there is an entire book devoted solely to the Peterson graph, which I mentioned at the beginning, by Holton and Sheehan. It's quite thick, so you can read a lot about it in this book. And now let me come to the conclusions. So first of all, I think we must distinguish between beauty of mathematical objects and beauty of visual representations of mathematical objects. Yeah. Since we have visualizations and we have abstract mathematical objects. Okay. Second conclusion. Visual representations of mathematical objects may be assessed for purely perceptual beauty. For example, a lay person can do that, a mathematician as well. Or for intellectual beauty, or for a combination of both. Yeah. When comparing diagrams of the Peterson graph, mathematicians respond to a combination of both visible symmetries and absence of irrelevant intersections, for example, or larger angles. When a layperson attributes beauty to a visual representation of an object, it is just perceptual beauty. Somebody who doesn't understand the meaning. When a mathematician attributes beauty to a visual representation of an object, it is at least partly intellectual beauty. The mathematician may be responding to perceptual features which directly represent mathematical features of the object. For example, visible symmetries. Or perceptual features which make it easier to comprehend the object. Few irrelevant intersections, for example. So here I draw a distinction between a lay person talking about perceptual beauty. So he say, somebody who is not a mathematician will say, beautiful picture, nice colors, nice harmonic structure. Okay. A mathematician could also appreciate these properties, these visible properties. But on top of that, a mathematician could appreciate how beautifully the drawing is organized, how beautifully a visual argument is organized. So it's quite rare in mathematical practice that it's not very easy sometimes to find a good visualization which helps to see the structure well. So mathematicians may react very positively to such a good, smart drawing, and they may call it beautiful. Yeah, that's it. Acknowledgements and some literature, some mathematical literature. Shall we stop here? Thank you.
Well, comments, questions? Stupid questions?
Why you look at me when you say that?
I didn't.
I have one.
Okay.
No. Yeah, we are. I'm sorry I'm late again, but as I think we are somehow considering the beauty of an object as a function of their symmetries somehow. And if that is right, then maybe we could say that the logical objects are the most beautiful objects, because there's this characterization of logical objects as the objects which are symmetric under every permutation of the universe, of the domain. For instance, if you take the universal quantifier, it is the second order predicate whose extension, the set of objects which satisfy it, is just the set, the domain itself. So if you make a permutation of the domain, it's still being the domain. So it's invariant under permutations. The same holds, for instance, for the existential quantifier, whose extension is the set of all non-empty subsets of the domain. So again, suppose the domain is just AB, then the existential quantifier is the set AB, the set A, the set B, and that's all. But this set, these three element sets, if you change AB, it's still the same, because AB is AB, A turns into B, B turns into A, but the set is the same. And conjunctions are just like intersections, and if you think of intersections as triples of set, intersection of the set, and if you take the set of triples whose third element is the intersection of this first two, then again this is invariant under permutations. And the same for complements. If you take a fixed domain and a set. And
so is your question about that? If we have, whenever we have a symmetry, it's a beauty. something like that.